All right, let's dive into some really cool research today. We're tackling grokking in deep learning. You know that kind of weird thing where a model goes from, like, totally lost to a total expert, super suddenly. Like it just had a eureka moment.
Yeah, and it really throws a wrench in everything we thought we knew about how machine learning should work, right? I mean, you expect gradual improvement, not these huge leaps in understanding, especially after it seems like it's been stuck for ages.
It's almost like it was just messing with us the whole time, pretending to be confused.
Right. And the thing is, it often happens with these tasks that seem super simple to us, like basic math problems.
This makes you wonder,
Mhm.
what's actually happening under the hood?
That's exactly what these researchers wanted to figure out. And get this, they found that this whole grokking magic might be less about actual learning and more about how computers deal with numbers, like on a really deep level.
Okay, color me intrigued. So the research mentions something called softmax collapse. That sounds kind of ominous.
It kind of is, yeah. So softmax is a function we use in neural networks to turn, the model's outputs into probabilities, basically how confident it is in its answer. But turns out when those numbers get really, really extreme, like crazy big or tiny, the softmax function it can basically break down.
So it's like those old calculators. You put in too big a number, and it just gives you an error.
Exactly. Except in this case, instead of an error message, we get this softmax collapse. And that's where tiny little errors in calculation, they start to snowball. And then they mess up the whole learning process. It's like these tiny gremlins just causing chaos behind the scenes. And it all leads to the model just hitting a wall, where it can't really get any better.
Makes sense. But why are the numbers going haywire in the first place? That's where naive loss minimization comes in, right?
You got it. Naive loss minimization, or NLM. It's like the sneaky villain in our story. It tricks the model into thinking it's doing great when it's not. Think of it like trying to get a lower golf score by just moving the flags closer to the hole. Your score might look good, but did you actually get better at golf?
Not really. Just found a sneaky way around it.
Right. And that's kind of what NLM does. It focuses on making the error, the loss, look smaller without actually learning the task properly. It's all about finding shortcuts. But those shortcuts aren't making it smarter. And the way it does that is by pushing those internal numbers to these crazy extremes. And then, bam, softmax collapse.
Ah, okay. So it's like a chain reaction. NLM leads to crazy numbers, which causes softmax collapse, and suddenly the model's totally derailed.
Exactly. It's this vicious cycle that can really mess with a model's ability to generalize, especially when you're working with small data sets where overfitting is already a problem.
Okay, so now we know the villain, this NLM. How do we fight back? I know weight decay has something to do with it.
Yeah, weight decay is like our first line of defense. Remember, weight decay tries to keep those internal values, the weights, from getting too big. And it turns out this simple trick actually helps counter NLM, stops those numbers from spiraling out of control.
So it's like weight decay is putting on the brakes, keeping the model from going too far down that NLM road.
Exactly. It's all about keeping those numbers in check and making sure the model's actually learning the task instead of just finding loopholes. And this is why weight decay has been so good at causing grokking. It's not just about simplicity, it's about keeping those numbers under control.
This is making me totally rethink weight decay. It's like a secret superhero. But if weight decay is just a fix, are there other, maybe more elegant ways to handle this?
That's where things get really interesting, because the researchers didn't just identify the problem, they actually came up with some really cool solutions. StableMax and ugrad. These could really change how we think about training AI.
Okay, now you've got me hooked. Let's start with StableMax. What is that?
So think of StableMax like SoftMax 2.0. It's like they took the original function and gave it a major upgrade, making it way more resilient to those extreme values that cause the collapse. It's like reinforcing that calculator to handle massive numbers without breaking a sweat.
So it can just handle those giant numbers without any drama.
Exactly. And here's the kicker. They found that StableMax could actually lead to grokking all on its own, without any weight decay at all.
Oh, wait, seriously?
Yeah, which is a huge deal because it means maybe grokking is a more natural way for these models to learn. It just needs those crazy numbers kept in check.
Whoa. So you're saying if we can control the numerical chaos, grokking could be, like, the default?
It's definitely a possibility. It suggests grokking might be an emergent property of the optimization process itself, not some weird side effect of specific techniques.
Mind blown. And you said there were two solutions. What about this ORGRAD?
Or grad. or orthograd if you want to be fancy. It's a clever optimizer that takes a totally different approach. Instead of letting the model fall into that NLM trap, orgrad acts like a guide dog, gently steering the model away from those unhelpful updates that just inflate the numbers.
Okay, I love that analogy. So instead of just blindly making its internal values bigger, the model's forced to actually learn the task.
Yeah, you got it. And the coolest thing is they found that this can lead to super fast generalization, often without any overfitting.
Wow. Orgrad is like a personal trainer for deep learning. Gets the model in shape super efficiently. So if it works this well on simpler tasks, imagine what it could do with more complex problems.
Right. What's exciting about this research is that it's not just interesting theories. They're giving us actual tools that could totally change how we train AI.
It's wild to think that all this came from understanding something as basic as how numbers work. But there's one last piece we haven't talked about yet. Remember that input representation thing?
Yeah, how the way we give the model data can actually make those number problems even worse.
Right. So tell me, how does that affect this whole grokking dance?
Okay, imagine you're trying to learn a new language. Would it be easier to learn from a well-organized textbook or from a random pile of words?
Definitely the textbook. Organization makes a big difference.
Exactly. And the same goes for these models. If you give the model a super detailed, high-dimensional representation of the data, like using one-hot encoding, it's like that jumbled pile of words.
So it's more likely to just memorize everything without actually learning the pattern.
Exactly, like trying to memorize the dictionary instead of understanding grammar.
Yeah.
And that can lead to overfitting and all those numerical problems that trigger grokking.
So we're accidentally setting the model up to fail by giving it data that's too complex.
Kinda, yeah. But we can fix it. By using lower dimensional representations, basically simplifying the data, we can actually help it learn more smoothly and gradually without needing that sudden grokking jump.
It's all about finding the right balance, giving the model enough info to learn, but not overwhelming it.
Precisely. And this just shows how important it is to think about how we prepare the data. It's not just how much data, but how it's structured for learning, like preparing a meal. You need the right ingredients and combine them the right way.
I like that analogy. So we've gone from grokking to this hidden world of numbers and now to how we present the data. It's like peeling back layers of an onion, getting more complex all the time.
And we're not done yet. There's still so much more to explore in this deep dive. Thinking about grokking being tied to how stable the numbers are, it really highlights something important about deep learning, something we often forget.
Yeah. We get so focused on the fancy models, the algorithms.
Yeah.
But sometimes it's the basic stuff, how the numbers are actually being handled that can really make or break things. It's like you build a rocket, but you forget to check if the fuel even works.
That's a great analogy. And that's what's so cool about this research. They're basically saying that grokking, this thing that seems so magical, it might just be the result of pushing those numerical limits too far. Like trying to do a crazy complex calculation on a calculator that's about to explode.
Makes you wonder, right? How many other weird things we see in deep learning are caused by these subtle number problems? Like, are we just scratching the surface here?
That's a great question. And honestly, it's something researchers are really digging into right now. But this research definitely shows us that there's a whole other layer of complexity going on. It's not just the algorithms, it's the basic math happening underneath.
For sure. It's like we're so busy building the fastest car, we forget to check if the tires can handle the speed.
Oh.
But speaking of solutions, one thing that really blew me away was how creative they were in coming up with solutions. StableMax and orgrad. Those aren't just band-aids. Those are totally different ways of approaching the problem.
Totally. You don't see researchers rewriting the deep learning playbook every day. So let's talk more about those solutions. What stood out to you about their experiments with StableMax?
Well, the fact that just swapping out the regular softmax function with StableMax actually led to grokking, right? In those classic benchmark tasks. And without needing weight decay, that just blows my mind. It really supports their idea that softmax collapse was the main problem the whole time.
Right. It's like StableMax just clears the path, lets the model learn naturally without getting tripped up by those number gremlins.
And remember how they found it worked, even when the weights got really big. That kind of goes against the idea that you need small weights for grokking.
Exactly. It's not just about the size of the weights. It's about how well they work together with all the other numbers in the model, like an orchestra, right? It's not about having the loudest instruments. It's about each one playing its part in harmony.
I love that. Okay, so StableMax is all about making softmax more robust. What about orgrad? How does it work?
eGrad's all about stopping that naive loss minimization in its tracks. Remember, NLM is all about making the error seem smaller without actually improving the model's understanding.
Yeah, like that golf analogy.
Yeah.
Looking good on paper, but not actually getting better. Or like using Photoshop to make your muscles look bigger instead of going to the gym. Not that I would know anything about that.
We all have our shortcuts, but eGrad says, nope, we're going for real gains here. It basically forces the model to explore other, more meaningful ways to learn by restricting the kinds of updates it can make.
So instead of just inflating the numbers, the model has to actually figure out how to make better decisions, like hit the gym for real.
Exactly. And get this, they found it often led to crazy fast generalization, no overfitting at all.
Wow. So eGrad is like the ultimate deep learning personal trainer, gets those models in shape super fast. It makes you wonder, if it works this well in simple tasks, what could it do with even more complex stuff?
That's a very exciting thought. And that's what's so cool about this research. It's not just theories. It gives us real tools that could change how we train AI.
It's wild to think that all this came from understanding something as basic as how numbers work. But, hey, there's still one piece of the puzzle we haven't talked about. Input representation.
Yeah, the whole thing about how the way we feed data to the model can actually make those number problems even worse.
Right. So tell me, how does that play into all of this?
Okay, so imagine you're trying to learn a new language. Would it be easier to learn from a textbook with clear explanations or from a random pile of words?
Definitely the textbook.
Right. The same goes for deep learning models. If you give the model a super detailed, high-dimensional representation of the data, like using one-hot encoding, it's like that random pile of words.
So it's more likely to get lost in the details and just memorize everything.
Exactly. And that can lead to overfitting and, yep, you guessed it, those numerical issues that trigger the whole grokking thing.
So it's like we're accidentally making it harder for the model to learn by giving it data that's too complex.
Kinda, yeah. But the good news is we can change that. By using lower dimensional representations, we can actually help the model learn more smoothly without that sudden grokking leap.
So it's all about finding that sweet spot, giving the model enough info to learn, but not overwhelming it.
Exactly. And this really shows how important it is to think carefully about how we prepare the data. It's not just about the amount of data. It's about quality and how it's organized. It's like prepping a meal, right? You need to choose the right ingredients, combine them in the right way.
I like that. So we've gone from grokking to this hidden world of numbers, and now to how we present the data. It's like peeling back layers of an onion.
And we're not done yet. There's still so much more to uncover.
You know, going through all this whole world of grokking and these numbers, it's kind of made me realize something.
Oh, yeah. What's that?
Even with all this super advanced AI stuff, sometimes the biggest breakthroughs come from, like, going back to basics, rethinking the simple things, the numbers, the algorithms, even how we organize the data. It's kind of humbling.
I totally agree. It just shows you that even though deep learning can be amazing, it's still built on these core mathematical ideas. And really understanding those can give us so much control and insight.
Yeah. We're so busy building these bigger, fancier models that we forget to appreciate the power of those simple parts. It's like we've been trying to reach the moon by building taller and taller towers instead of focusing on rockets.
And what's great is that this research doesn't just give us a deeper understanding. It gives us actual tools to fix these problems. StableMax and OrGrad. They're not just theories. They could totally revolutionize how we train AI.
Totally. It's one thing to point out a problem. It's another thing to come up with solutions that actually work. And that's what makes this research so important. It's like these researchers went to the deep learning doctor complaining of a headache. And instead of just getting a Band-Aid, they got a whole new brain.
Huh. I like that. It really shows the power of combining a deep understanding with a knack for problem solving.
So where do we go from here? What does all this mean for the future of AI?
Well, for me, the most exciting thing is the possibility of unlocking even faster and more reliable learning. Imagine models that can generalize from just a few examples. Models that learn complex stuff in, no time. It's mind-blowing.
It's almost like we're on the verge of AI that learns as quickly as humans. That's incredible.
It is. This research also makes us rethink how we measure how well deep learning models are doing. If grokking is actually a more natural way of learning, then our current metrics might be totally wrong. Those long plateaus where the model seems stuck, maybe those aren't failures. Maybe it's a sign that the model's about to make a huge jump.
So instead of getting discouraged, we should be excited when we see those plateaus. It's like, yeah, it's always darkest before the dawn, right?
Exactly. We need better ways to measure performance that capture the subtle things going on. And I think this research shows how important it is for different fields to work together. This breakthrough came from people who understood both machine learning and numerical analysis.
It's like combining a chef and a chemist, right? Delicious food and a deep understanding of the science behind it.
I love that. So, to wrap up this deep dive, I think the biggest takeaway is don't underestimate the power of going back to basics.
Totally. Whether it's the numbers, the algorithms, or how we organize data, those little details can have a huge impact,
Yeah.
even with the most advanced AI.
And never stop questioning what you think you know. Grokking was a mystery for so long because it challenged everything we thought about how machine learning works. This research is a perfect example of the power of curiosity, careful analysis, and thinking outside the box.
Well said. So, one last thought-provoking question for our listeners. What if we could really master this whole numerical stability thing? Could we create AI that doesn't just mimic human intelligence, but actually surpasses it? AI that learns and solves problems in ways we can't even imagine.
That's a fascinating question, and one that I'm really excited to see answered.
We encourage you to explore these ideas more. Share your thoughts. The world of AI is always changing, and it's through explorations like these that we'll keep pushing the boundaries. Until next time, keep diving deep.